Hello and good morning to everyone. So today's lead code question is 762, which is prime numbers of sat bits in binary representation. So in this question we are given two integers left and right, and we have to return the count of numbers in the range from left to right, and we have to include left and right also, and the count of number in this range that have a prime number of set bits in their binary representation. So what does that mean? Suppose we are given 21, so 21 is represented as 10101. So how many set bits are there? Means how many bits are there whose value is 1? So 3 bits are there, and 3 is a prime number, right? So this is one possible answer, right? So this way we have to check all the numbers from left to right. See, let's see this example to understand it more clearly. So 6 is represented as 110. So 2 set bits. So 2 is prime number. So this is one answer. Here 3 set bits, one answer. Only one set bit, but one is not prime. So this won't be an answer. Here 2 set bits, so this is an answer, and this is also an answer. So if you have noticed, from 6 to 10 there are 4 numbers uh, that has the count of their set bits prime is 4, right? Now see the next example. In next example we are given numbers from 10 to 15, right? So in 10 we have 2 set bits, and 2 is a prime number. So this is an answer. 3, this is also an answer. 2 answer, 3 also an answer, 3 also an answer. This has 4 set bits, so this is not an answer. So total 5. So total 5 numbers are there that has the prime number of set bits. So if you'll see the constraints, our left element and right element can be up to 10 ki power 6, and right minus left is up to 10 ki power 4. So these constraints are useful in formulating the approach, because we have to check from left to right. So the number of elements is only 10 ki power 4, and see here at max right is 10 ki power 6, and 10 ki power 6 can be represented in less than 20 bits. So the constraints are useful, so we'll be formulating our approach from these constraints only. So let's see our approach 1. So in approach 1 what we'll do is we directly simulate, that is we count the set bits brute forcely. So as 10 ki power 6 is less than 2 ki power 20, so we at max we can have 20 bits in an element, right? So what we do is first we find prime numbers up to 20 and store them, because when we get count of set bits, then we have to check them whether they are prime or not. If they are prime, then we will be increasing the answer by 1, right? This is what we have to do. So, and also right minus left is less than equal to 10 ki power 4. So even if we iterate from left to right, so then it will take time complexity as big of 10 ki power 4, and then finding set bits in each number will take big of 20 time. So the total time of this approach is big of 20 into 10 ki power 5 4, that is 2 into 10 ki power 2 into 10 ki power 5, right? So this is a feasible approach. Now what we check next is how to check the set bits. How to check the set bits in a number, like how many bits are 1. So what we do is, let's say the number is this 1011001 in binary. So to check the whether the first bit is 1 or not, what we do is, if we do n and 1, if we do n and 1, and if it is 1, then that means the first bit is 1. If it is 0, means the first bit in n is, this lowest significant bit in n is 0 only, right? So if it is 1, then we increase count by 1, right? Else the count will remain same. And then what we do is we right shift the number by one position. So suppose when we right shift this number, then what we get is we get 101100. We have shifted this one to the right position, right? So we get this number. Then again we check 0 and 1 is 0, means it is not a set bit. Again when we right shift, this will be removed. Again 0 and 1 is 0, so again we have right shifted 1 and 1, so it is 1, so we increase count to 2. Then right shifted 1 and 1, increase count to 3, right shifted, then 0, count remains same. So and then this one, so it is 4. So if you notice that there are 4 set bits only here. So and we keep doing this thing until our n is greater than 0. If you don't want to do this approach, you can also use the inbuilt function to count the number of set bits. So let's see the code. So we have stored all the prime numbers up to 20, because 10 ki power 6 at max take 20 bits, sorry, less than 20 bits to represent 10 ki power 6. So even if 10 ki power 6 has all the set bits, so it can at max have 19 bits. So to check whether those bits are prime, we have stored all the prime numbers up to 19, and then what we are doing is we are iterating from left to right, and we are counting the number of bits in the number, in our current number, and we are then checking whether this count of bits is present in this prime number or not. If it is present, then we are increasing the answer, and at the end we will be returning our answer. So after this we will see one more approach of finding the number of bits which is faster than the previous right shift bits. So if you'll see the time complexity of this code, which is 2 into 10 ki power 5. So let's see a faster version to find the number of set bits. So earlier what we were doing is we are doing n and 1, and then we were right shifting by 1 bit. So the time complexity of this approach is the total number of bits, total number of bits present. But this approach, that is Brian Kernighan's trick. So this approach will take the time complexity of total number of set bits, that is the total number of bits whose value is 1. So in this what we do is we take the n, and then we do n and with n minus 1, right, and store that in n and increase the count by 1. So what this n and n minus 1 will do, so it will remove the lowest set bit, and at the end we store the return the count. So what this Kernighan's method does is like it every times remove the rightmost set bit. So let's see the same example that we have seen above. So in above case it has taken big of 7 time, but see here it will be taking only 4 operations, that is big of 4. So let's see how is it working. So initially n is this number, so what is n minus 1, this is n minus 1. So when we do n and n minus 1, so n and n minus 1, if you are noticed, the rightmost set bit, that is 1, has removed, and we have increased our count by 1. Now our new n is this, that is 10110000, and n minus 1 is this one will be made to 0, and these all zeros will be converted to 1, this is n minus 1. Now if you again do n and n minus 1, you have noticed that this rightmost set bit has been converted to 0, and then our count becomes 2. Similarly for this set bit, and then at the end for this set bit. So in big of 4 time we get all the set bits, which earlier was taking time of big of total bits, right? So this approach is faster than the previous approach. In this what we have to do is we have to do n and n minus 1, and this value that we get, it will becomes our new n, and we have to increase the count every time. So this is a simple approach but faster than the previous approach. Let's see the over approach 2 for solving the question. So what we can do is we can use mask to check if the number of bits is prime. Earlier what we are doing is we are storing prime numbers in an unordered set, and then we are checking whether the number of bits is prime using that set. But here what we do is we will make a mask where all prime indexes are 1. So we know the prime indexes are 2, 3, 5, 7, 11, 13, 17, 19. So we take a mask of 19 bits, right? And we mark these indexes as 1 and all the rest indexes are 0. And let's say our bit count is 5. Suppose our current bit count in a number is 5. So what we do is we left shift the 1 by bit count number. That is we get this value. That is we have shifted 1 at the 5th position. And then what we do is we do AND operation with the mask value of this left shifted value, right? When we do AND operation, as you already know that in the mask we have make the 5th bit as 1, right? We have make the 5th bit as 1. So 1 and 1 will give us the answer as 1. That means if bit 5 in mask is 1 means the result is non-zero. Then that means this 1 less than 1 left shifted by bit count, or this bit count is a prime number, right? Else if it gives us a result 0, then that means it is not prime number. So let's see first how we'll be making the mask. So see, in mask what we are doing is we are marking every prime numbers bit as 1, right? And then what we are doing is we are iterating from left to right, counting the number of bits. Here we have used the faster approach, right? And then what we are doing is we are here we get the count of bits, and then we are left shifting 1 with number of bits, and then doing AND operation with our mask. And if this result is non-zero, then we are increasing our answer, and at the end we will be returning our answer. So I hope I am able to explain you both the approaches and both the way to find the number of set bits properly. So if you like the solution, please make sure to like, share and subscribe the channel. Thank you.